Hey guys, welcome to my channel. This is Omolo the Great. If you're new to this channel, remember to subscribe, share, and like this video. And don't forget, hit the bell button so you can always get a notification about my upcoming videos. If you missed the previous videos, please, you can review. I've attached links to this video. So, body fluids. So, simply, what do you understand by body fluids? It's the fluids within the body. The constituents within the body, literally, you will actually have what we call, especially the water, makes a very big component of fluid in our body, and also the ions make another important component of fluids in our body. So why do we need to study these body fluids? Why do we need these body fluids in our bodies? So there's what we call the significance. According to our coverage today, we shall look at the significance of these body fluids. We shall look at the body fluid compartments, and under each we shall see the classifications and the volumes, and then we shall look at the composition of each compartment. We shall look at how these volumes of the different compartments are actually determined, and then we shall attach some clinical correlates to our discussion on body fluids. So why do we need to know about these body fluids? One, body fluids are significant in playing a role in homeostasis. Okay, so for example, you get very thirsty, you're water depleted. What do you usually do? You're going to take some water, okay, so to restore the state of the body. So it plays a homeostatic role. Water is also very important because we remember most of the metabolic processes that take place in our bodies actually take place in an environment full of water. And then we also have different nutrients that are required in the body, and these nutrients usually are moved in a suspension of blood, and blood has a big fraction which is water. So this water, or this big component body fluids, plays a very big role in transport of nutrients, okay, within the body. But also when we looked at the cell, we said the cell has the cytosol, and that cytosol is largely a component of water. And this cytosol actually plays a very significant role in establishing the texture of the cell. So this water or body fluids play a very big role in actually establishing the texture of our cells within the body. All right, let's dig deep into understanding these body fluid compartments. So you talk of if you talk of body fluid compartments, body fluid compartments. Okay, so all we want to understand here is we want to locate the different segments, or what we are calling the compartments, the different parts of the body that actually where water is encased, okay, or where these fluids in this body are located. So that is what we are interested in understanding. So from our brief, maybe biology or our brief background, you realize that if you look at our vessels, okay, so this is an illustration of our vessel. This is a blood vessel, okay, as we are seeing here. And then in this blood vessel, it has a lot of fluid within, okay. The fluid component of blood within the vessel is actually called plasma. And then we have another component of fluid that is located within or outside the cells, okay. So the environment outside the cell. So we have fluid that is within the blood, which is the plasma, okay. And then we have this section B, okay. So this is A that has plasma, and then B is the environment around the cells. And so this is what we call the interstitium, okay, the interstitium. So the interstitium also has water. Then another, if you see this other area that I've called C, this makes up the inside environment of the cell, and which we are calling the intracellular, okay, intracellular compartment. Okay, so from this illustration, you can actually see that we can locate the areas where water or these body fluids are actually found within our body. So one, we have within the plasma, as we've said, the interstitium, and then within the cells. Okay, so to add terminology to this, the plasma and the interstitium make the environment that is outside the cell, as we can see. So if they make the environment that is outside the cell, so implying that they make up what we call an extracellular environment, not so? So we locate one compartment of fluid, which we are calling the extracellular fluid compartment. And then the other environment that is within the cells is what we are calling the intracellular fluid compartment. So literally we have two broad categories of our body fluid compartments. So as I'm trying to highlight here, if you see, we have what we call, this is the intracellular fluid compartment that spans from here up to here, and then we have this, the other, that's making up the extracellular fluid compartment. Okay, so the total amount of water that is found, or fluid that is found within the intracellular and the extracellular, that makes up the total amount of water that is within our bodies, and that is called the total body water. This is what we call the total, this, okay, will be the total body water. So literally we can see that actually our total body water is a summation of the intracellular fluid compartment and the extracellular fluid compartment. Okay, so we see, and we have seen from here, from the environment that is outside the cells, is what is actually globally called the extracellular fluid compartment, implying that it's actually divided into two. We have the plasma, and also we have the interstitium. Okay, so this is what, so when we divide, so this is what we are calling the ICF, and then this is our extracellular fluid compartment, which is composed of two things. We say we have the interstitium, okay, interstitium, and then we have the plasma. Okay, so if you in dividing or classifying our body fluid compartments, literally this is what we have. We have what we call the environment that's within the cells, which is the intracellular, and the environment that's outside the cell, which is the extracellular fluid compartment. And these two, especially the extracellular, is divided into other two smaller compartments. One, we said we have the interstitium, and then we have the plasma. Are we together? So here we can see we've classified our body fluid compartment. So we want to see that what is the amount, what is the volume of each of these compartments. So some mathematics has been done by previous scientists, and I've tried to make life very easy for us to establish this. Okay, so one more thing not to forget. In a 70 kilogram male, usually about 60% of his body weight is actually water. Okay, so but you will see that actually there are some variations that usually occur, where you find a male will have more total body water than a female. And what accounts for these variations? This is because the females will have more fat or adipose tissue compared to males. If you look at the histological arrangement of the adipose tissues, they literally have less of water that is within the cells. Okay, so you find they're very, very compacted with a lot of adipose. Okay, so if in simple terms, we also know that actually where fat is hydrophobic or water hating, not so. So in the adipocytes, we expect to have less of water. That is simple understanding. So implying that where if you are in a state where you have a lot of fat, implying that you will have less total body water. So variation in total body water, one is sex, where you find males and females will have some variations or distinction. And what explains this is the difference between their adipose tissue. And then we also see that actually age can bring about variations in the total body water, where you will see that actually a young child, okay, for example, a neonate will have about 80% of his body weight is water, okay, compared to an adult male that we've said who is about 60%. So you find the variations. You find the neonate will have more total body water compared to male, and this is because still the neonate will have less fat, and they're still very young. They have less solids or tissues compared to an adult male that has built a lot of mass and tissue. Another variation sometimes is actually in the lean body mass. So if you find a lean person, okay, so who implying they have less fat, they have more muscle, so they'll have more total body water compared to an obese or someone who is overweight. Okay, so those are very important to remember. So variations in total body water, we said we have variations in age, variations in sex, and also variations in the body mass. Okay, so when we come back here, we said 60%, so implying that the total body water in an adult male, which is 60%. Okay, so 60% is the total body water in an adult male. So we want to know what percentage will the intracellular fluid compartment constitute, and what percentage will the extracellular fluid compartment constitute. Okay, so in fractions, so we shall see that actually this total body water of 60% is the same as 3 out of 3, which is actually 1. Okay, so then this okay, so this, the intracellular fluid compartment, you've realized that from my illustrations, the intracellular compartment, I've been drawing it much larger than the extracellular fluid compartment. So what does this imply? So we imply that there is more total water that is found within the intracellular fluid compartment compared to the extracellular fluid compartment. And that is why fractionally, in a fraction of 1, we attach 2/3 of this fluid is found within the intracellular fluid compartment, and only 1/3 will be found within the extracellular fluid compartment. Okay, so this is where we shall put from our illustration, we find this is going to be 2/3 of this, of the total body water will be ICF, and then 1/3 of the total body water will be the extracellular fluid compartment. So also remember that 60% makes up about 42 liters. So here we are trying to elicit the volumes. Okay, so we want to know what is the volume composition in percentage, and what is the volume composition by what proportion or fraction, and what is the volume composition in liters. Okay, so this is just some basic math which if you're watching, you would really be interested in getting your calculator and maybe to do this, because when you do it, you will not forget. Okay, so here what you do, we want to get the percentage composition. What proportion in percentage is the ICF? What proportion of the total body water in percentage is the ICF? So this becomes just 2/3 of 60. Okay, so this is 60 by 2, which is 120 over 3, to give you about 40%. Okay, so 40% of the total body water is intracellular fluid volume. Okay, and then literally, so it is quite simple. If you then subtract 60 minus this, it will actually give you 20%. And also if you say 1/3 of 60, you'll actually get 20%. So 20% of the total body water is the extracellular fluid compartment. So this is equal to the fraction of the extracellular. This 1/3 is equal to 20%, and this is equal to 40%. Okay, so how about in liters? So in liters, if you say 2/3 of this 42, okay, 2/3 of 42, if you do the math, will actually give you 28 liters. Okay, and then you can actually do the subtract here, you get about 14 liters. So implying that the 1/3 and 20%, this is equal to, in liters, it's 14 liters. Okay, and then this is equal to 28 liters. So you need to remember this. If they ever ask you something about these body, the volumes, you can express them in liters, whereby about 42 liters of the total body water, and then 28 liters found within the intracellular, and 14 liters that are found within the extracellular fluid compartment. So we also say that extracellular fluid compartment is subdivided into 2 other smaller compartments, where we have the interstitial compartment and the plasma compartment that's found fluid within the vessels. So this, let's also do the math. Okay, so here we are having the extracellular fluid compartment, which we said is a summation of the interstitial and the plasma, okay, the plasma component. So we establish this in form of quarters, okay. So 4 out of 4, which is also 1, which makes up the extracellular fluid compartment, will make this interstitium will take 3/4 of the extracellular fluid, and then this will take 1/4 of the extracellular fluid, okay. So what is it in percentages? We already said the extracellular from here makes up 20%, okay. So what is this 20%? If you say 3/4 of this, you'll have to get about, the interstitium will take about 15% of the extracellular fluid compartment, and the plasma will take the balance, which is 5%. Okay, so implying that 15% of the extracellular fluid compartment is interstitial fluid, okay, and 5% of the extracellular fluid compartment is actually plasma. Now, how about in liters? We say this is, we have said the ECF makes up about 14 liters, okay. So 14 liters, 3/4 of this will give you about 10.5, okay, and then 1/4 of this will give you 3.5. So this in liters, so implying that this in volume, so this is 3/4 and this is 1/4, which is also equal to, this will be 5% of the ECF, and this will also be equal to 15% of the ECF. This is equal to 3.5 in liters, and this is the same as 10.5 in liters. Okay, so this is very, very important. So you can always generate this by yourself if you really understand the different proportions and the fractional percentage distribution in each of the compartments. Okay, so we are done with the body fluid compartments and we have established the volumes. So it's important for you to remember those figures, or you can actually derive them by yourself. Next, let's look at the composition. When you look at the composition, we want to know, we say we have a lot of water, but we also have ionic composition. We have different ions that are distributed within the extracellular fluid compartment and the intracellular fluid compartment. So in the extracellular fluid compartment, you will likely find the cations, especially sodium. You'll find calcium and some anions like chloride and bicarbonates. Okay. Whereas in the intracellular fluid compartment, the cations, we have potassium, you find magnesium, and then you find some anions like phosphates. Okay, these phosphate compounds. So these are very, very important because the distribution of these ions will help us to understand the different concepts when we reach excitation of muscles and when we are discussing muscle physiology. So this is important, and each of these has different ranges, and it's important for you to actually remember. So that's briefly about the composition of these compartments. Then let's see how these volumes are actually determined by each. For the body fluid compartments determination, we want to determine the different volumes of the body fluid compartments, and we want to know how are they determined. So the principle behind this is actually understanding the different markers that are used in determination of the body fluid compartments. And these markers are actually unique in physical properties. They have unique physical characteristics that make them unique to determine a specific or a given body fluid compartment. For example, let's look at some of those markers. So for the total body water, okay, so total body water. So there are markers that have been used for studying total body water. Here we have, especially it's called isotonic water, okay, isotonic water. And this isotonic water could actually be, we have examples like deuterium water, and also we have tritiated water, and deuterium water. Then for the extracellular fluid compartment, we have, there are some sulfates that are used, but commonly we have mannitol and another molecule called inulin. Okay, and then for the plasma, we have what you call radioiodinated serum albumin. Okay, so we have a radioiodinated serum albumin. Okay, but you can also use also what you call Evans blue dye. You can use Evans blue dye. Then for the intracellular fluid compartment and the interstitium, there are no determined or well-known markers that can be used for determining this. So what we can actually do, if you have the total body water, which is the extracellular fluid compartment plus the intracellular fluid compartment, you can actually get the intracellular fluid compartment. So ICF will actually be the total body water minus the extracellular fluid compartment. So if you want to get the plasma, rather the interstitial, the volume in the interstitium, okay, this we can get it by we know our extracellular fluid compartment, which we can determine, and also we know our plasma. So we subtract the plasma volume. Okay, so this we can get the interstitial volume. So the principle behind each of this is very, very simple. The principle behind is when a marker is introduced within the body or within the compartment, for example, total body water, we expect this marker to be able to dissolve or to distribute all through all the compartments. Okay, so for example, if we are determining the total body water, the marker we are using should be able to distribute. Usually what you do, you introduce maybe through phlebotomy, introduce the marker through in circulation of the person, okay, and then we are going to measure. So the first thing is we choose an appropriate marker. If you want to determine total body water, we choose an appropriate marker which has a characteristic, or it should be able to diffuse or distribute all through the compartment. So if this is where marker we are using, maybe deuterium water, it should be able to distribute within the plasma, distribute within the interstitium, and also be able to distribute within the intracellular fluid compartment. So there we can get this. That marker can actually give us a big idea or an accurate idea of the total body water. So if we want to do the extracellular fluid compartment, we want to determine the volume. What we need to do is the marker we are using, for example, mannitol or inulin, the specific property of this marker is that it should restrict to only the extracellular fluid compartment. For example, if we introduce mannitol, it should be able to distribute within the plasma and within the interstitium. Okay, so we said extracellular is made of the interstitial and the plasma. So that should not be able to diffuse into the cells. So it should not enter the intracellular fluid compartment. And then for the plasma, the markers we are using, maybe Evans blue dye or RISA, this should all be able to distribute and stay within the plasma and should not diffuse or distribute within the other cellular compartment. So that is an important physical property that should be applied to each of these. So step one, as we determine, you have to determine or to choose an appropriate marker. Okay, so the second thing, when you introduce the marker into the body, okay, you give it time to equilibrate, you give it time to distribute and equilibrate. But under normal physiological mechanisms or processes, when you take in fluid, okay, the kidney has an interplay, a role. So we get some renal losses in form of urine. So you're going to introduce a known volume of a marker into the body, but that marker we also know the concentration. Maybe I've introduced 5 mils, okay, that's the volume I've introduced. Of concentration, maybe 20 milligrams per deciliter, okay, and I'm introducing maybe we are determining the extracellular fluid volume, and I've introduced mannitol. So a known volume, this is the total volume I've introduced. After equilibration, there is some renal losses in form of urine, and so then the concentration, this does not change. So eventually, to determine the volume of the compartment, the volume of the compartment. This will be equal to, we want to know the amount, okay? How much amount is within the body after equilibration, and then over the concentration of that marker. So the amount that is within is it's a result of one. We want to know when we instill what has been taken in, what has been what we have given, okay, minus the renal loss, or what is lost in urine, now over the concentration, implying that when we give 5 mils, we may lose maybe 2 or maybe 3. We may lose 3 mils in urine, for example, implying that the amount that we shall remain with will actually be 2 mils. And this is the volume, this is the amount of this marker that is within, that are distributed and is within the compartment. So we just divide it by the concentration, and we are able to determine the volume of that compartment. So it is as simple as this. You need to know the physical characteristic of the marker so that you make an appropriate choice of the marker. 2, you choose the marker depending on its physical characteristic, and then when you introduce, you need to factor in the renal loss, and there you can divide by the concentration, because the concentration will not change within the body. All right, that is it about determination of our different body fluid compartments. Okay, so and now we move to something called we want to understand our clinical correlates. So under this, we want to understand that if I introduce, if there's any change or disturbance within the body, what happens to the different volumes of the compartments? What happens to the change in osmolarity? So there are two principles that we need to remember. One is going to be the principle of, we need to know the different volume. So a volume of a compartment is largely dependent on the amount of solute that is contained within that compartment. For example, in the extracellular fluid compartment, there are ions we talked about. For example, sodium, which makes up salt and its chloride, maybe sodium chloride. We can also have sodium bicarbonate. These salts determine how much fluid will be present within the compartment. That's principle number 1, you should not forget. Principle number 2 is the osmolarity. Okay? So the osmolarity determines the direction of fluid shift. Okay? So it determines the fluid shift, whether this fluid will shift from the intracellular or this fluid will shift to the extracellular fluid compartment. This direction or movement is determined largely by the osmolarity. Simply put, what is osmolarity? Osmolarity, refers to the number of osmotically active molecules expressed in milliosmoles per liter. So you've heard of terms of osmolarity, okay? Osmolarity and osmolarity. Osmolarity, okay? So there's one with L and there's one with R. So osmolarity, this is R. We are this concentration, the amount of osmotically active substances are expressed in milliosmoles per liter. Okay? So the easiest way to remember is R for R. You see this osmolarity in liters. Okay? And then for osmolality, now it will be the opposite. We are expressing this in milliosmoles per kilogram of water. But experimentally, actually, these two things mean the same, because 1 kilogram of water is equal to 1 liter of water. So the terms are sometimes used interchangeably. Okay, and mathematically, osmolarity, if you get you usually get it to get osmolarity is equal to twice the sodium in milliequivalents per liter plus the glucose out of 18, and then the blood urea nitrogen concentration out of 2.8. Okay, so this division 18 is just to convert the milligrams per deciliter concentration of glucose to milliosmoles per liter. Same thing with blood urea nitrogen, divided by 2.8 to convert it to the standard units for osmolarity, which are milliosmoles per liter. Okay, so this is something about osmolarity to remember. We said it determines the direction of fluid shift. Okay, so if the osmolarity of in the ECF increases, implying there are more osmotically active molecules, or maybe solids, or maybe you have a lot of sodium chloride here. What happens? The osmolarity here increases. Okay, so fluid from the intracellular has to shift and move to the extracellular fluid compartment. Similarly, in the opposite, if the osmolarity extracellular fluid compartment falls, then fluid actually will have to shift from this extracellular to the intracellular fluid compartment. So those are two main important principles we need to remember. So let's apply these principles to the different conditions, and we see how they affect and can tell us the different disturbances. So this table is going to help us to understand and we dissect this concept of disturbance in body fluids. Okay, so we said the osmolarity will determine the direction of fluid shift. So here you have the different conditions. The change, you shall be observing a change in the extracellular fluid volume, the intracellular, the osmolarity change, and the form of disturbance. So this will be in the form of, if you have a change in osmolarity. Osmolarity change can stay the same, which is isosmotic. It can decrease, which is hyperosmotic, and can actually increase, which is hyperosmotic. The volume can stay the same, or volume can increase, which if it stays the same, I'm using this term to mean no change. Or when we have an increase in volume, that becomes a volume expansion, and we have a decrease in the volume, it becomes a volume contraction to that compartment. So let's look at each of these conditions. So let's start with diarrhea. So you understand that in diarrhea we're having a lot of fluid loss from the GIT. Okay, so what's important to remember about diarrhea is that the amount or the osmolarity of the fluid that is being lost within the GIT is actually isoosmotic, or it has the same osmolarity to that of what is in the ECF, or to that of plasma. So we don't expect a change in the osmolarity. That is why the osmolarity of the ECF does not change. Already it's qualifying this to be an isoosmotic. There is no change in osmolarity. So what happens? Already we're having no change in osmolarity, and then our extracellular fluid compartment, the volume is actually going to decrease. Okay, so this is our ICF and this is our ECF. Fluid is being lost from here, irrespective of no change. There is no, and the fluid loss is isosmotic, which means it has the same osmolarity or between the extras like that of the extracellular. So implying that irrespective of the amount lost, there will not be a fluid shift, because we say osmolarity change causes or determines the direction of fluid shift. So no change in osmolarity, we don't expect exchange of fluid between these two compartments. But because of extensive fluid loss, we expect a decrease in the extracellular fluid volume. And then definitely, because there is no fluid shift between these two, because of the same osmolarity, there is no change in the ICF. Same thing for burns, they take in the same category. So sweating, another peculiar thing about sweating is that the amount or the osmolarity of sweat, when we are sweating from the skin, the osmolarity of this vapor or steam or whatever way you want to call it, this osmolarity is hypoosmotic, okay, to that of the extracellular fluid compartment. So implying that because it is hypoosmotic, which means the fluid being lost from the extracellular fluid compartment is having a lot of water. So we're having a lot of water lost, okay, from the extracellular fluid compartment, okay, and this fluid loss is hypoosmotic, implying that it's losing a lot of water and leaving a lot of solute behind. Okay, we're having a lot of solute left behind. It's similar, for example, if you decide to mix some salt in water and then you decide to boil it, what's going to happen? You're going to lose a lot of water, and then eventually you will remain with salt back. And that's what happens even in sweating. You're losing a lot of steam, which is full of water, and leaving the solid behind. And so that's why eventually the osmolarity of the ECF is going to increase, because we say we are losing the water and leaving solid. Osmolarity increases. This qualifies this to be hyperosmotic. Okay, because the osmolarity is increasing, definitely, and we say we are losing a lot of fluid, so the extracellular fluid volume does what? Comes down. So because of the difference between the osmolarity in these two compartments, because we've lost a lot of fluid here and the osmolarity is actually high, fluid has to leave the intracellular to the from the intracellular to the extracellular, and then eventually after equilibration the volume of the intracellular also decreases eventually. That's why we are calling it a hyperosmotic volume contraction. That is clear. Same thing happens in diabetes insipidus. So we're having problems with ADH secretion. So we are not absorbing a lot of water, not so. So we are losing a lot of water in form of urine, leaving a hyperosmotic environment. And that's because we have lost a lot of water. ECF volume decreases, and then this has to compensate during equilibration. High salt intake. When you take a lot of salt, introduce a lot of salt within your extracellular fluid compartment, the osmolarity is going to increase. Because the osmolarity has increased, this causes fluid shift from the intracellular to the extracellular. So the volume of intracellular is going to decrease as the extracellular fluid volume actually increases. Infusion of isotonic sodium chloride. Isotonic, this is the same concentration of sodium chloride. And so this concentration or osmolarity will be synonymous or equal to the osmolarity of the ECF. We don't expect, so there is no change in this in osmolarity within the extracellular fluid compartment. All we are doing now is adding water, okay? So we're adding, the volume of the extracellular is going to increase. And because there is no change in osmolarity, we don't expect any fluid shift. So there is no change in volume of the intracellular fluid compartment. Syndrome of inappropriate ADH secretion. So in syndrome of inappropriate ADH secretion, still we are having a lot of ADH that is being produced. And then too much ADH that is being produced, we're having a lot of water that is being reabsorbed. Too much water that is being syndrome of inappropriate ADH secretion. We're having a lot of ADH that's being secreted, okay, from other sources within the body. So too much of water is going to be reabsorbed. When too much of water is reabsorbed, the osmolarity is going to fall, because we're going to have solid molecules in excess of water. So the osmolarity is expected to actually fall. The volume, because of this increase in the ECF, actually the volume has to do what? The volume has to increase. And because of the increase in the volume, coupled with the decrease in osmolarity, already we see there's a change between the ECF and ICF osmolarity. Osmolarity of the ECF is actually low, implying that it has more water compared to the ICF. So eventually the ICF osmolarity becomes a little higher than the osmolarity of the ECF. So therefore fluid has to shift from the ECF to the ICF. So eventually you're going to have expansion of both compartments. And that's what we are calling a hyposmotic volume expansion. And then finally we have adrenal insufficiency. So this affects the functioning of the adrenal gland. Importantly to this, we are going to talk about mainly aldosterone. So problems with aldosterone secretion. Aldosterone plays a big role in reabsorption of sodium chloride. So because there is a problem, the sodium chloride a lot of it is being lost in urine. Therefore, the osmolarity in the ECF is going to fall, implying that we have more water in excess of the solids. Okay, more water compared to the solids. So osmolarity has to fall. Because the osmolarity has fallen, we expect a change, or we expect a fluid shift because of the difference in the osmolarity. Okay, so fluid, we have the ECF has fallen, and then in the ECF, the osmolarity has fallen. Okay, but you remember that where sodium is, water follows. So sodium is moving out through urine, water is also following through urine. Okay, so eventually we expect a volume decrease in the extracellular fluid compartment. Okay, So because of the change in osmolarity between the ECF and the between the ECF and the ICF, this osmolarity decreased. Okay, it decreased, so there was excess of water in compared to the solids. Because of that change is what caused a shift of some fluid from the ECF to the ICF. So you expect a volume, an increase in the volume of the ICF, coupled with that decrease of decrease in the volume of the ECF, following the fluid that will be following the loss in sodium chloride. Yeah, so this brings me to the summary and the conclusion on our body fluid. It's important to attach clinical relevance to each of these. Yeah, so I hope you've understood. Please remember to subscribe, like, and share this video. Don't forget to hit the bell button so you can follow through the next notifications for the next videos. Thank you. Bye-bye.